Our first speaker is going to be Sebastian Oriolo, who's talking about the Gondwanide Orogen in southern South America. And I'll just pass you over to him now. Thank you.
Okay, thank you. Thank you very much for being there. I will show you today the state of the art of our research and some preliminary results on the metamorphic and structural architecture of the Gondwanide Orogeny in southern South America. This is mainly in the Patagonian region. And as many of you may know, this Gondwanide Orogeny is one of the main orogenic features for the late Palaeozoic of Gondwana, so particularly in this case of Western Gondwana. Among other things we are working on in this area, I will focus in this talk mainly on the reconstruction of PT-VT paths in the metamorphic basement. So, oh yes, now. Okay, here you can see on the left a very sketch distribution of the main domains, let's say, of Patagonia. This is between Argentina and Chile to the west. So we have the Andes in this area, the so-called North Patagonian Cordillera or North Patagonian Andes, and to the east we have the North Patagonian Massif, and to the south the Southern Massif. So the main motivation of this work is to reconstruct the large-scale tectonic and geodynamic evolution of these orogens, which is actually a strongly debated topic since the early 80s. Early proposals, as you see here on the right, are related to consider the Gondwanide Orogen as the result of a collision, in this case, of Patagonia as a single plate with the rest of Western Gondwana during the late Palaeozoic, whereas alternative models also consider like a two-stage collision, so collision of the southern part, also collision of the northern part in different moments. In recent years, some alternative proposals indicated a possible relationship just with subduction or, for instance, accretionary processes, such as for the case of island arc complex accretion. So this is still a hot topic, and therefore we will focus mainly on the reconstruction of the metamorphic and structural evolution of the basement rocks. I will show you mainly data from the northern part, where actually studies in the last, let's say, 20 years have focused essentially on igneous rocks, so mainly dating, geochronology, and isotopes and geochemistry of granitic plurals, which are widespread in the areas you can see in this map, with ages between the Carboniferous and the Permian. And also in the last decade, quite a lot of new data came out, mainly on the Untitled Chapter data from the metasedimentary rocks. Nevertheless, reconstruction of the metamorphic and structural evolution of the basement are actually very rare, and particularly linked with petrochronology. So this is why we are emphasizing this aspect. So I will start first with some results from the northern, from the western part here in the Andes, and I will go in a roughly west-east transect, then to the western part of the massif, and finally to the eastern part of the massif. So if we start in the Andes, we have very nice evidence of progressive deformation, in this case by polyclinal faults. So we have F1 isoclinal faults refolded by a second generation of isoclinal faults, this F2 you see here. And if we look at the microstructures, the record is very comparable. We see this widespread S2 foliation, which is very well exposed in the field, but locally we also see relics of an older folded S1 foliation, in this case within a plagioclase porphyroblasts. Here in this GX map image, the situation is very comparable, so we see relics of S1, but in this case within a garnet porphyroblast, which we use, as you see here, the changes in the color, the result of variable different compositions. So we use the zoning of garnet for PT estimations together with the mica and plagioclase compositions. In addition, we also use these tiny monocytes you have here, LMS2, to provide phytochronological constraints on the timing of metamorphism. As a result, we reconstructed this PT evolution, this prograde path associated with the development of these S and F fabrics, and making some assumptions on the bulk rock chemistry and considering the allanite monocyte equilibrium, we interpret that the ages we obtained with the monocytes, mainly around 300 million years, actually record conditions close to peak metamorphism, or also likely the retrograde nearly isothermal decompression, because most part of the prograde evolution is actually within the allanite stability field. And therefore, we would interpret that, let's say, this age is a minimum age for the prograde path, and therefore the whole evolution may be essentially restricted to the late Carboniferous. When we started, we were thinking about, of course, subduction modeling for the PT estimation, but we got quite a lot of evidence, surprisingly, of post-metamorphic metasomatic processes. So if you check here, this is one example of monocyte ages of the basement itself, where we have very nice evidence of Jurassic and Cretaceous overgrowth. But the most convincing evidence came from fluid inclusion data, as you see here, where we found one particularly rare mineral, which is ferropyrosmolite. This is an iron-rich mica, which after heating, in the heating stage, gives rise to this green amphibole, which according to Raman spectroscopy may have a ferroactinolite to chlorohastensite composition. In any case, we can be more or less sure that we need certainly to have some calcium and iron metasomatism in these metamorphic rocks, possibly related to these Mesozoic processes, and therefore we cannot guarantee the basic assumption of preservation of the bulk rock composition. So we have to be very careful if we want to apply here to the subduction model, and therefore we stick actually to the conventional barometry. But besides this metamorphic basement, we also have very nice poodles in the area. I will show you afterwards which is the most common fabrics, but in the basement itself, we also have, as you see here in the poodles, very nice northwest to north-northwest fabrics, metamorphic fabrics, which are comparable to those recorded here by the Plutons, in this case, magmatic fabrics. As you see here, we have very well preserved magmatic layering, in this case, gabbros and diorites, and also locally you see this shape preferred orientation of plagioclase and amphiboles, which define very nice magmatic foliation. So we see that these Plutons, which also have zircon ages close to the late Carboniferous, have a nearly comparable fabric to coeval metamorphic sequences exposing as part of the war, let's say. If we go to the western part, the North Patagonian Massif, I will show you first some data from here, and in the next slide some from the northern part around here. So the situation is more or less the same. We have here this gray area, a metamorphic sequence with very nice monocyte ages, also with Carboniferous, though there are also some Devonian ages preserved. And if we go here, we have also very nice Plutons, synkinematic Plutons in place contemporaneously with shear zone development also during the late Carboniferous. And as I showed you before, here fabrics both in the Plutons, in the shear zones, and in the host rock are also roughly northwest strike. I encourage you tomorrow to check for the poster from Renda, who will give you more details on the data from this section. And if we actually check or try to see, let's say, the big picture here, we can see that this area is aligned along a large scale northwest belt with the Andean exposures I showed you before. This is very well documented by geophysical data of Renda and collaborators in tectonophysics. If we go to the northern part of the Western Massif, we have again very nice evidence of regional metamorphism, in this case under relatively medium pressure conditions and high temperature. You can check also tomorrow for the presentation of Paul Marcos on this area. And similarly to the previous areas, we also have very nice evidence of magmatism, and in this case, there are also some migmatites. The main difference is that in this area, most igneous and magmatic record is restricted to the Permian, so it's slightly younger than in the previous regions that I showed. And finally, if we go to the eastern part of the North Patagonian Massif, near close to the Atlantic coast, we have also a very well documented petrochronological record in monazite. In this case, this is a compilation of individual monazite ages from around 4 samples. We have a very well constrained middle to late Permian metamorphism, as you can see here. And the evolution, the PT evolution, is also comparable to that we saw in the Andes, though pressure conditions, peak pressure conditions, are slightly lower, so around 9 kilobars. Here, this was done by conventional thermobarimetry, but here we're also working on the subduction model. So as you see, this is part of an ongoing research. And if we put all this information together, and we just give you a brief overview, there is no need to call for a collision. We can reconcile all this evidence into a more simple yet likely model of advancing mode subduction. So if we check on the geology of the basement in Chile, it's something I didn't show, but anyway, it's quite well known from the literature. We have very nice evidence of accretionary complexes of late Carboniferous to Permian ages, forward sequences such as the Western series. And once we get in the Andes and in the western part of the Massif, we may be looking, for instance, at the Orogen core and the magmatic arc. So this crustal thickening and compression, or actually transpression, from what we get from the fabrics, it may imply that progressively this origin migrated towards the retroarc. So we have this late evidence already during the Permian in more, let's say, retroarc positions. And the final advance of the origin and the formation is recorded even further east in the Ventania system. It's something I didn't show, but we can discuss afterwards, which is a region quite well known due to correlations with the Cape Belt in South Africa, where we get the low-grade deformation and metamorphism already by the late Permian, more or less in a retroarc foreland position. So as you see, these are only very few things that we have done, and there is still much work to do. We're also working on the dating, on the isotopic signature, the geochemical features of the intrusions, also on the Eutratus zircon of the sedimentary and metasedimentary rocks. There is still a lot of work to do. So if someone is interested, we are always happy to join young people to the team to work in this sketchy area, which is Patagonia. So thank you very much.
Thanks, Sebastian. That was a really interesting talk. We'll just see if any questions are going to pop up in the chat. Haven't got anything yet. Oh, here we go. So a question from Catherine. Do you have problems with your monazites yielding a spread of ages which are challenging to interpret in terms of the PT history, or where your TE inclusion relationships are helpful to interpret?
Yes, we had some problems, especially, for instance, with these late overprints, these Mesozoic overprints, which in some cases just erased the Paleozoic history. So we combined not only the ages, but also the geochemistry, so the mineral chemistry of the monazite to distinguish between different populations and these different ages. Also for to distinguish, we also use the microstructures, which were also quite helpful we found very contrasting microstructures, for instance, in the case of the Monazoic and the Paleozoic, the Mesozoic and the Paleozoic ages. But anyway, in many cases, all these constraints were not enough. So we have to be very careful and try to get independent lines of evidence to interpret Monazoic ages. So in some cases, we got very complex patterns of zoning, which were quite tricky to interpret. So we keep on working on that.
Thanks again, Sebastian. We don't have time for any more questions, but I'm sure people can ask them in the chat if they have any.